Hello, everybody. It's a beautiful day, beautiful Boone day. And I want to ask you today for the attendance, please answer this question. What's your favorite local hiking spot or recreation spot? Wondering if there's anything y'all know that I don't know about. My favorite is Little Lost Cove. If you haven't been there, it's really amazing. Let me know and I'll try to get you some directions. Okay, and yeah, I forgot to create a video of fitting a histogram in Python. So I will do that. It's on my list. Sorry, I forgot. It will happen and I will upload that soon. After I finish grading the exams. It will definitely be done by the end of the weekend. Do we have questions? Okay. Alrighty. So last time we talked about curve fitting. What is the point of curve fitting? Why do I care about curve fitting? And the answer that I focused on was, finding the fit parameters. That's what we were talking about last time. So our example last time was we measure the speed of light a bunch of times. We measure it 10 times at 10 different distances with 10 different times of flight of a laser pulse. And we find all those corresponding speeds of light and we could average them, but it is superior. It is a superior thing to do to instead fit those points with a curve. And then out we get these fit parameters. And those are, it's not just like we're doing a fit for fun. We want those fit parameters so we can use them in our calculations to actually state our measured speed of light. So we do the fit to convert our measurements into our final quantity. And that's probably something you experienced in intro lab and now maybe also in the lab for this class. You'll definitely see that in senior seminar. That's kind of the main focus. Not kind of, it is the main focus of Physics 4210. For you to collect data and convert the data into some final value by doing some kind of fit. So at this point in this class, we've pretty much learned everything you need for senior seminar. You could totally tune out and not worry about learning stuff for senior seminar at this point. Not that you'll do that. You're all great students, but just letting you know to kind of maybe help you chill out a little bit. Okay, did I cover what I was going to talk about? Yes. Okay. Yeah, we're going to go back to this curve fitting FET. This was fun, but we didn't really get to use all the buttons yet. So we're going to do this again. I'm going to put in some values. We're pretending like we measured these values here. And yes, there are error bars here. Why do we only see error bars in the y direction here? Who can tell me why? If you're talking, Ethan, I can't hear you because I think you're muted. Or maybe you weren't talking to me. Okay, anybody?
Yeah. It's because for this system, the x value uncertainties need to be negligible.
Yes, thank you, Allison. If we are doing a linear least squares regression in the first place, it is basically a rule that those x value uncertainties have to be really small compared to the y value uncertainties. So it's inherently true that that is the case if I'm doing a linear least squares regression. So that's why those are shown here to reinforce that concept. They're not actually being used to do the calculation, just to verify it's a valid curve fit scenario. So I'm going to put a curve. There's all my values. I'm putting a curve. And right now, because this is linear, we have selected linear to do a linear fit. We have a slope and we have a y-intercept that is corresponding to the best fit. So the best fit, we can also see, corresponds to the highest r squared value and the lowest chi squared value. So let's talk about what these values are here. The Zoom thing to go out of the way. Okay, so I found this kind of illustration that helps us understand r squared a little better. R squared basically is how far apart are the values from the curve. It's a measure of how far away. What's that scatter value? Scatter factor. So on the left-hand side here, we have an r squared situation where the r squared is 15%. And then on the right-hand side, the r squared value for this situation is 85%. So it never is over 100%. You have 0, between 0 and 100. So the best you can get is 100. And if you have 100, that means every single dot is perfectly on the curve, like perfectly on there. And if you have a very low r squared value, that doesn't mean it's necessarily bad. That just means it's kind of spread out a lot. It means you might have a lot of like random noise. And if you repeat your experiment a bunch of times, you can maybe shrink that a little bit. But you're still measuring the middle of it, so it's not really necessarily a bad thing to have a small r squared value. Okay, what is chi squared? Well, if we push this little information button, it tells us what chi squared is. So chi squared is really used more frequently for polynomial fits, which we will talk about today, which is described on a page in your book I'm about to tell you. Page 193 is section 8.6, least squares fits to other curves. So besides lines, you can use linear least squared for other curves, for polynomials, for example. And this quantity is really more, it's not just for linear situations. As you can see, f down here is the number of parameters in the fit. So it's basically like the order of the polynomial. Or close to the order for a polynomial. Anyway, so this chi-squared value is equal to the y value on your curve minus the y value of your measurement. So this difference between the curve and the measurement for x sub I divided by the standard deviation squared. Oh, sorry, that quantity squared divided by the standard deviation squared. Add those up. Divide by n minus f, number of points minus parameters, and that's your chi-squared value. So it's basically a measure of the distance of each point from that curve. It's basically like a measure of the residuals the sum of the residual. It's like it's really similar to the equation we were minimizing last time when we set up that equation and took the derivative and set it equal to 0. It's really similar to that. Basically like a sum of the residuals with some other factors. So what's fun about this bet, besides that I can just do what I already did, I can also, instead of doing a best fit, I can adjust the slope of my fit line. And I can manually adjust my y-intercept. This is so fun. So I can try to tilt my line to make it the best fit, to make it like as parallel to that line going through the, points as possible. And then I can adjust my d value to get it to fit better inside those points. And while I'm doing this, my r squared and chi-squared are changing in real time. And if I want to get the very best fit, I'm going to, of course, move my y-intercept down to go kind of through the middle and adjust my slope to get the smallest chi-squared, which I think we are there now. Pretty close to the best fit. So that just wanted to give you kind of a visual representation of what we're doing with all this. It just looks like, linear algebra on the slides if we don't also show what's going on. I mean, maybe you can just see it in the linear algebra. Maybe you're a genius and you can do that, but I'm not sure I would be able to. Closing out. Any questions about curve fitting? Okay. We looked at some Python code last time, and I wanted to point out this funky outlier. Oh, that's not the right one. Yes. Okay. This is what I showed you yesterday. I made up some Tuesday. I made up some speed of light data and accidentally put the wrong exponent on this one. So it was like really a weird data point. So that's basically an outlier. And so I went back and fixed it to see how much would it change my fit. So when I did my fit, you can see that the fit does a pretty good job of going through these points, but then it seems like this outlier is kind of pulling up the curve where it should be kind of down, more in the lower region going through those points down there. And I mentioned last time something about a better fit means more accuracy. So I wanted to make sure I was clear. That's not always the case. What I meant was a better fit gives you a higher confidence that this number that you're calculating is correct. Just based on the fit. It doesn't necessarily mean your final value is more accurate. You have to apply that number you get from the fit to find the final value correctly. So just wanted to clarify that. Okay, so I went back and I made a new data set. I have to wait for this thing to move out of the way. Come on. The new data set was just like the old one, except I changed in my Excel file. This was 7.19 e to the minus 9 before. So I changed that to minus 8 now. So I basically made the outlier not an outlier anymore. And I took that data file and dragged and dropped it into here. So there it is, data 2. and I took my old code, linear least squares speed of light, and over here, I right-clicked that and hit duplicate. And I took the exact same file and duplicated it and renamed it linear least squares speed of light less outlier. So in case y'all didn't know you could do that, I'm just showing you. That's a possibility. And then I just put data 2 here and like ran the whole thing over again with the new code, with the new data set. So we can do that again. There's the new data set. It has the -8 here instead of the -9. And now here's a bunch of formatting and importing libraries. And more formatting. Okay, and now we're setting up our axes. And here's our new plot. So that looks a lot better than the old plot with that strange point that was like random and obviously wrong. So looks a lot better now. Our new fit looks like this. So we can see that the line goes through the points a lot better. I didn't calculate chi-squared or r-squared, so that'll be something I tell you next time. We have a new value for the speed of light, 3.17 e to the 8, where it was 2.81. So like I said, this is not necessarily a more accurate, for sure, value for the speed of light, but we do have a better confidence now. We can tell that the line is closer to all the points here than it was here. So we can have a higher confidence that our new value is more correct just based on the fit and based on the data, not necessarily correct compared to the real speed of light. All right, any questions about that? All right, we'll be ready to do your own curve fitting here in just a few minutes. I will be asking you to do that in your breakout rooms. Okay, hold on just a second. Sorry about that. All right, okay, we're gonna go back to our PowerPoint slides that we were looking at the other day. Show. And we left off with basically 2 equations down here, the first one for A, and on this slide, this one for B, where A and B were our fit parameters from the very beginning. They were the slope and y-intercept of our fit line for our one-dimensional polynomial. So we applied these linear algebra techniques and were able to solve, like create an equation to solve for A and B to find those fit parameters. We did not talk about the uncertainty in each of those values, nor in the uncertainty in the y values. So as far as the standard deviation, as far as the uncertainty for the fit values for the y sub I values are those that are on the fit line. We have this equation to describe or to that is equal to the standard deviation, which is our stated uncertainty for the y values when we do a linear least squares regression. So y sub I here is the y value of the fit. A is, I'm sorry, it's the y value of the data point, A is that y-intercept, B is the slope, x sub I is the x value for the data point. We sum up the squares of those and then divide by n-2 and take the square root. That gives us our standard deviation. The uncertainty for the value A for that y-intercept is going to be the standard deviation times the square root of the sum of the x sub I value squared divided by this quantity delta n times the sum of x sub I squared minus the sum of x sub I squared. Delta was actually the denominator of B and of A. So that's also written as delta sometimes, the A for the A and B values. Okay, and then for B, the uncertainty for the value B, that slope, is going to be the standard deviation, which is equal to the standard deviation of B, basically, is equal to that standard deviation for each y value times the square root of n over delta. Okay, so that is how we determine those uncertainties. Any questions? Okay, so as we said, the linear least squares technique can be used for nonlinear cases. A special case is exponential because you can take an exponential and turn it into a line, basically. You can just plot it differently, and then if you plot it differently, it's a line, and then you can fit it with linear least squares. So let's consider this function y equals a e to the bx. It's an exponential function with b as our coefficient and our exponent, and a as our coefficient out front. We can take the natural log, of both sides. The natural log of y, there that is. If we take the natural log of this, we're going to take the natural log of the first thing times the second thing, which is equal to the natural log of a plus the natural log of e to the bx. And the natural log of e to the bx is just bx. So we have converted our exponential function into a linear function that we can fit with linear least squares. You take the natural log, you do a normal linear least squares fit. There's nothing really different at all. You just convert your function into a linear function. Okay, there are other nonlinear cases as well, like polynomials that we talked about earlier. In our FET, we could have chosen linear least squares to do a quadratic fit or a cubic fit, which wouldn't make sense since that looked linear anyway. So we can try to set up something that is more quadratic looking and see if we can get a quadratic fit for that. I don't know. Maybe that's not a great parabola. But if we try a quadratic, we definitely have a better I-squared and R-squared value, as I was trying to make it actually quadratic in the first place. So how do we actually do that with linear least squares? How is the math different if we're using this same kind of technique? And it's really not that different. We just have bigger matrices to solve. That's all. So for example, let's say we have this polynomial, y equals a plus bx is the one we've already done. Now we're tacking on a cx squared plus a blah, 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 up to h x to the n, some arbitrary coefficient times x to the n. If I consider this function, if I'm trying to use this as my function, as my model, my equation that matches my data, then, and I'm using linear least squares, then I basically make a matrix here that is n plus 1 rows long or down. And my corresponding matrix or vector over here, column vector here, and column vector here are going to be n rows down. And so I just have a bigger matrix than I did before. Before, my matrix was a 2 by 2. That's the smallest you're going to get for your first order polynomial for y equals mx plus b. The higher order your polynomial, the bigger your matrix and longer your column vectors are going to be. But you do the same idea, basic idea to find those coefficients. The fit parameters are now going to be a, b, c, and all of those coefficients for each term in your polynomial. And so you'll have to try to solve for those a, b, c, etc. When you do this math. So let's look at a case of a quadratic. So we have only added c as an extra parameter now, an extra fit parameter that we're trying to find. So the next most complicated case after the one we already showed. Then our residuals in that case are going to be a plus bxi plus cxi squared minus y sub I quantity squared. And we basically want to add those all up and take the derivative with respect to each fit parameter, with respect to a, with respect to b, with respect to c, and set those equal to 0. Each of those is going to convert into one of these equations down here, where we will be able to eventually solve for a or b or c like we did in the previous steps. We use a 3 by 3 instead of a 2 by 2 in this case. And we take the determinant to solve and find what a, b, and c are, which I'm not going to show here. But that's the basic idea behind the algorithm that's happening when you use a computer program to do this. Questions? Then it's breakout room time. Here's the breakout room question. You're going to need Python. I mean, I guess you could do this by hand, whatever, but I would recommend Python. And I'm going to try to, I don't know, I'm going to put this as a file in the chat. So let me do that first, and then I will put breakout rooms. And okay. Do we have an answer? Anybody? Final result. Not enough time.
44.
44. I got 45. How'd you get 44? Whoever said that?
Well, I didn't do it in Python. I used Origin instead.
I used Excel. I totally cheated.
But I used Origin and I've used the and I used the formula that they gave us. I plugged in the values that were that it had given me for it gave me the values of well, in Origin it calls it A1, but that's pretty much the same as V0. Oh, but you did a linear fit. Okay, I did something completely different.
Yeah, so I took the values that were given, which are shown here, 10, 20, 30, 40, 50, and the corresponding times, or whatever that was, V of t, the counts, sorry. And I put those here. And then I took the natural log of the counts in this column here, natural log. So I converted this equation. Basically, I took the natural log of both sides, and in my Excel spreadsheet, what I need to be able to like graph is the natural log of those, natural log of those y values. So I put the natural log in this column and the time in this column, and then time is on my x-axis for my graph, and natural log of the counts is on my y-axis for my graph, and I put in a linear fit with Excel, which uses linear least squares, and got minus 0.0222 for the slope. And we can see that the slope here is, sorry, I'm going over time a little bit here. The slope is the slope times t is our like x value, right? So the slope is minus 1 over tau. That's like the coefficient in front of t. So the coefficient in front of x is the same thing as the coefficient in front of t here. And so I took 1 over 0.0222 and got 44. And so Ethan, you did a different fit, I guess, an exponential fit, but got a similar answer. So anybody else get a different answer?
We also got 45 in Python.
Awesome. Thank you, Jess. Okay, cool. All right. Well, I think we get the point, and I've talked too long, and I'm sorry. And I hope you have a great weekend, and I'll see you next week.
Hope you have a great weekend too.
Thanks, Alex. Bye, everybody.
Bye.
Bye.